So, welcome to lecture 16. This is going to be mainly on bipolar junction transistors. It'll be the first lecture on bipolar junction transistors. Just a couple announcements before we start. So, homework number 6 is online. Well, we'll be online soon and due Friday 2 weeks from now via Gradescope. And so I say online soon because I'm actually recording this lecture well before the date of this lecture, which is supposed to be the October 4th Friday lecture, because I will be traveling on Friday. Continuing with announcements, lab number 3 continues next week. Next week, your pre-lab will be due before the lab next week, and you should finish that lab next week. You also have your first midterm on October 11th, the Friday. We have 7 to 9 p.m. for this midterm. It's going to be in 160 Krober Hall. In the last lecture, I talked about the ground rules for the exam, and that information is also up on the web under the exam quiz link. We're going to have a review session as stated on that information sheet for the exam, but the review session is going to be on Tuesday from 6 to 8 p.m. In 293 Corey, and the GSIs who will be leading that would ask you to please post on Piazza specific problems you would like covered at that review session. If they don't get any problems, they'll just, I guess, choose a few there, but it's much better if you let them know which things you're having the most difficulty with. And these could be problems on the midterm that I passed out last time, the old midterm, or on your homework problems, or whatever you may have. And so I've said this several times, but my Monday office hours will move to 5 to 6 p.m. on October 14th and thereafter. I guess I will not have office hours this coming Monday, October 7th, because I will also be gone that Monday. And so this lecture is pre-recorded, and so will the Monday lecture be pre-recorded. I will be back on Wednesday, October 9th. So all right, so let's get on with this lecture. So last time we almost finished with MOS physics. I have one last thing that I want to cover, which is MOS CV curve. That's a capacitance voltage curve. After this, then we'll head into bipolar junction transistors. Like MOS transistors, they have regions of operation. They have a cutoff region, but then some of the other regions are named differently. So another one would be the forward active region, and we'll get to that region sometime this lecture as well. Okay, so let's just first start off with that the last MOSFET topic that I want to discuss, and that is the CV curves. So, MOSFET CV curves. And I should also mention that for this lecture, since it's a recorded lecture, I'm going to do the MOSFET CV curves sort of in real life. But when I get to the bipolar junction transistors, since I'm not really lecturing in front of anyone, I think what I'm going to do is just splice in the lecture from last year. So I want to tell you that because in those lectures you might hear questions and that sort of thing, and so you won't have to wonder, okay, who's asking questions when he's sitting there all alone doing the lecture. I won't be. I'm basically splicing in last year's lecture. That also will be a little more informative to you because some of those questions could be very good. All right, so let's talk about these MOSFET CV curves, and for that, let me grab this, which is our MOS transistor that I've been using several times over now. Oops, there it is. Okay, so we've talked about this device as a device that we can use to control current, and that definitely is what it is. So in this device, we're controlling the current that goes across this channel using this voltage VG, and more specifically in a circuit, we'll usually be talking about VGS for an NMOS device like this here. But when we want to talk about this device, we also talked about the fact that, you know, we have a gate polysilicon here, which is conductive. We have an oxide let's do that in green. We have an oxide between that polysilicon and the silicon on the other side. And so the silicon in this case, it's an NMOS device, so that silicon is going to be a P-type silicon. So I'll just say here this is a P-type silicon substrate. And the conductor of the gate, the oxide, and the conductor that the silicon is on the other side make up the capacitor. And so what I'm interested in doing right now is treating this device as a capacitor. So if I were to look at this as just a capacitor, what kind of capacitors am I looking at? So specifically, what does the CV curve look like? So I want to plot down here a plot of capacitance versus voltage. And that would be voltage applied to the gate of this device. So I can do this. And so for this, let me go ahead and apply some biasing to this. So let's ground out both the VD and the VS, or the VD could be, a very small voltage. Keep it in a linear region for now. And then for VG, what I'm going to do is just apply a voltage to that VG and measure the capacitance that I get as I change that VG. So here I'm just going to want to apply plus minus some VG voltage there to that. And so as I'm doing that, you know what occurs in this. So the first thing that occurs when VGS is very small, and this is in the cutoff region, so say when VGS is 0, so I can come down here and say at 0, what is this going to look like? It's going to look like something where I have a depletion region, as we talked about. So I'm going to have a depletion region around my source and drain, but I'm also going to have a depletion region underneath my channel, right? And so to create that depletion region, I'm basically pushing away holes from the surface near the gate, right? So as we talked about, you end up with negative static charge here. And so this negative static charge, it's charged there, but this is an insulator here. So in effect, if I were to think of the capacitance that I have, I kind of have a series combination between, let me do this in another color here. I guess I'll do that in red because it's most visible here. But I'll have a series combination of capacitors at first. I have first this capacitor here, which is the oxide capacitor. Then I've got this capacitance, which is the depletion region capacitance. So right here I can call this Cox. We've kind of talked about that capacitance. But this capacitance here, I can call C depletion. Okay? And so that C depletion and that Cox, I could sort of plot on this CV curve here. And so I didn't finish this. This is going to be sort of the capacitance that I see associated with the gate. And this down here is going to be VGS, or just VG in this case, because both the source and the drain are grounded. And so when I'm at 0 here, what I'm looking at is a capacitance that is a combination of two capacitors, and I guess one of them is going to be Cox, so I'll just write Cox in right here. That's Cox on this capacitance scale. And the other one is going to be some depletion capacitance. And as you know, as I increase this gate voltage, this depletion capacitance will keep increasing in size here. In other words, the depletion region will keep increasing in size until I get some maximum depletion region size, at which point inversion starts happening in this channel. And so I can plot on this sort of the capacitance associated with my maximum depletion region size. And when I do that, I have a series of capacitors like that. So I have this picture. I have a Cox, and I have what I'll call C depletion max. And so when I have this series combination of capacitors, I'm going to say that occurs somewhere here. Okay, so this capacitance is that right there. Okay, and so now I can try to analyze this. When I have 0 volts on my gate, which is right here, I have the series combination of Cox and C depletion. So series combination of capacitance, right? That's like a parallel combination of resistors. Whichever the smaller capacitor is sort of the one that's going to win, right? So if I take Cox and C depletion in series, what I'm going to get is something like this. Let me write that up here. So if I take Cox in series with C depletion, that's going to be equal to Cox times C depletion divided by Cox plus C depletion. It's like the parallel combination. They combine like a parallel combination of resistors would. And so in this case, right, if this is C depletion down here, the maximum C depletion, I guess that's not the maximum, it's the minimum C depletion, because that's when this thing gets has the largest depletion width here. That's right, I should call it the minimum C depletion, so I was saying it wrong before. Then any other C depletion here is going to be greater than that C depletion. So you get a series combination of a capacitance of Cox plus some C depletion capacitance that's greater than the minimum C depletion. And so that means the capacitance I'm going to get is going to be somewhere around here. Okay? And so you know that as I increase my VGS, what's going to happen is this is going to get bigger. Right? So this is going to move out. I guess I'll show that in brown here. Right? That moves out to, say, something like this. No, not necessarily that will change, but this will change here. Right? We're going to add static negative charge there, and so that's going to move out. So basically what that does is it creates a capacitor that is inversely proportional to a larger WD, right? And so if that's the WD for the case when I have a larger VGS than 0, and this is the WD, maybe I'll draw it right here. For the case where VGS is 0, then this is going to be smaller than that. Okay? And so if WD is smaller than, if the green WD is smaller than the brown WD, then the brown WD is basically means I'm decreasing my capacitance. So if I'm plotting this capacitance here, and then I can say the brown curve here, this is decreasing. So this is going to do something like this from that point. And it's going to decrease all the way down to this point here, to the point where I have my minimum depletion capacitance. But right at that point, that's where the channel will invert. Okay, so if my channel inverts, what's going to happen? I guess I'll do that in red here. If that inverts, what's going to happen is I'm going to form an inversion layer. Right? And so if I form that inversion layer, what's going to happen immediately is that all of this is going to rise to the capacitance just being Cox, because now that inversion layer is right there, and my capacitance is really between the conductor of the gate and that inversion layer. So that means if I project out Cox here, this curve will basically just come right back up. It'll come back up fairly quickly here, straight up to that capacitance. Okay, and then under certain circumstances, it'll just stay at that capacitance as I keep raising VGS. And you know, this happens again at the threshold voltage, so that would be at voltage VTN. Okay, and say I have some, you know, VGS prime. If I have applied something like VGS prime to this, then all of the area under this curve will be my total charge. Right, so this will be the charge Qn, which is the electron charge in the channel, or even the positive charge that's in the gate now that I put on the gate. This is just going to be equal to whatever Cox is times VGS minus my threshold voltage VTN. Okay? And so this part right here, where I have this depletion region brown, right, if I kept reducing my voltage, this thing would keep going up like this. Okay, and it will finally also get to COPS in a region that we're not really going to talk about in this class, but I'll at least name it for you. This is accumulation. This is where we have a layer of holes. At the silicon oxide interface. So right in the channel. It's not an inversion layer, but it's going to be a layer of holes there. And so this here corresponds to when we get our inversion layer. And remember, for an NMOS device, the inversion layer is going to be of electrons. Okay? And so this is what the capacitance versus voltage curve looks like when you're just looking between the terminals VG and either VS or VD going to ground there. And when you think of this capacitance, right, what I'm basically doing is I'm saying that this COX looks like some static dielectric, but this C depletion, the dielectric can move. But for capacitance, what you really need is an AC signal across that. So what I'm really doing is, say I took the case where, we're right at this point here. And I guess I don't have enough colors for that, so I guess I'll do that in blue here. So say I'm right at that point there. What's really happening is I'm modulating charge here, and I'm modulating charge there. Okay? And so that's why that AC charge is changing at those edges there. And this charge is changing because I'm pushing holes in and out. This charge is changing because I am putting positive charge in and out due to the polysilicon, doped polysilicon, almost metallic type layer there. So the capacitance that I'm getting here is really between these two spots right there if I'm looking just at that particular point. Okay? And so in the end, the capacitance that we're looking at is consistent with the classic definition of capacitance. It's going to be dq dV here, which in this case, when it's inverted, when we have inversion, this ends up being dqn dV. And this only happens when the inversion charge can keep up with frequency. So I told you the inversion charge can keep up with frequency if we have an N+ junction there. But if we don't have an N+ junction looking right there, then we may not actually get this inversion charge in this CD curve. But that's something for a later class, 130. So all this that I'm showing you here is really just to say that the capacitance in the end, like the main point I'm trying to make is that the capacitance of my gate, seen across the gate, is going to be a function of the gate voltage. Okay, which means that it is now one of these nonlinear, more generalized capacitances that we've been talking about. So just another aspect of the MOS device that you ought to know at this point, and that you would learn a lot more in EE130. But at least for now, you've got a little bit of an introduction to this. I'm not sure that there's not enough time for you to understand every nuance of this here. You'll see it again in 130 and in 143. And so with that, that's what I want to say about MOS physics. We may come back to talk a little bit more about the capacitors for MOS devices here. We're going to be concerned about mainly the capacitance and the overlap right here. I guess I'll just point at it here later on. So this capacitance right here, which is going to be what we'll call CGD, and that's going to affect the frequency performance of our transistor circuits later on. But for now, let's leave that till later on, and let me now move toward bipolar junction transistors. And so just to start out, bipolar junction transistors, these are the transistors that are actually used in the op amps that you're using in your lab. So the 741 op amp, which is one of the workhorses of op-amps out there is based on bipolar junction transistor technology. And I should say bipolar junction transistor technology, at least for silicon in many respects, is an older technology. For some of the 3.5 and other types of technologies, they're still using bipolar junction type topologies, but these days MOS in silicon is the most widely used everywhere. So you see MOS in especially your digital CPUs and that sort of thing. But you need to understand both of them, because again, your op-amps are based on bipolar junction transistors, and later on when you encounter circuits that are using a lot of these things, and I should say there's a lot of op-amps now based on MOS as well. But in order to understand virtually any transistor circuit out there, you need to understand both of these devices. So this is why we will now go into bipolar junction transistors, and I'm going to do that, like I said, by just splicing in one of my older lectures. So let's talk about bipolar junction transistors. And so that's abbreviated BJTs. Okay, so first, what is a bipolar transistor? And I think the best way to do this is just to tell you what physically it is. And so I'm going to make a drawing like I usually do that it doesn't look exactly like the way the transistor really looks, but it gives you the gist of what the transistor is made out of. And so it's a semiconductor material, and it's using things that you already know about. So it's basically using N-type semiconductor and P-type semiconductor, except the way that you make a bipolar transistor is you take N-type material, and that material you call the collector. You'll take P-type material and put that right up against that N-type material. So that's the base. And then you'll put N-type material, but I'll make it N+, which means it's going to be heavily doped here. And this will be the emitter. Okay? That is an NPN transistor here. And so let me go ahead and put some metal contacts on this. Okay, so that's metal, as it's been in past drawings. And the way that I'm going to operate this transistor is I'm going to put several voltages on it, and it's a 3-terminal device, just like the MOS device was before. So this terminal up here is the collector terminal, which I'll label C. Terminal below is the emitter terminal, which I'll label E. And finally, my base terminal I'll label B. And so what you'll do is you'll put voltages across this. So the voltage that I'll put across here is maybe a VBC. And then down here, I may apply a VBE. And that then attaches down to the emitter. Okay? So that's my bipolar transistor. And that physically is what it looks like from a semiconductor standpoint. But when you actually use this transistor, you're going to see it as a symbol. And so the symbol that this is going to take is one that maybe you've already seen if you looked at the data sheet for the 741 op-amp, but that's my symbol there. Okay, and so I'm going to have a base terminal here, a collector terminal up there, and the emitter terminal, where you can see that the emitter terminal is where the arrow is. And for an NPN transistor, which is what this is, NPN, the emitter arrow goes out and down in this symbol. Okay, I'm showing you that because later on I'm going to show a PNP device. And so in this I could put my same voltages here, plus minus VBC, close that up there, plus minus VBE, close that up here. Okay? And so I can also define some currents going into this. So currents, usually the collector currents defined to go into the collector, the emitter current is often defined to go out of the emitter, and the base current defined to go into the base. So I could show those same currents up here in this picture. So there's IC, there's IE, and there's IB. Okay, and what you're noticing here is what I've mentioned already, but all these are back-to-back diodes. Okay, I'm really just putting diodes back-to-back, and if I do that, then I can identify my diode. See, there's the P, there's the N. There's one diode. Okay, and then on the other side, I got the P and N there. There's another diode. All right, they're back-to-back diodes, and because of that, I can call these diode junctions. And so usually the junction between the base and the collector is called the collector base junction, which will abbreviate CBJ. And the other junction is the emitter base junction. Which we're abbreviating EBJ. Okay? So that's an NPN transistor. At the same time, there's a dual to this. Just like there's a dual to the MOS transistor, there's a dual to this NPN transistor, and that's the PNP transistor. And so down at the bottom here, I'm going to draw a PNP transistor, but actually I'm not. I'm just going to cheat. And just grab this and just turn things around to create my PNP transistor. If you're taking notes, you're going to love this. But don't worry, you have all these notes, of course, right? There you go. Out of nowhere. Right? So now let me fix this to create a PNP. So if it's PNP, of course, I'm going to want to change these. I'm still going to have a collector, a base, and emitter, but actually, for PNP, the emitter has the higher voltage. Okay? So think of this as the higher voltage being at the top and the lower voltage being at the bottom. That's usually always the way you're going to see it for circuits. When we actually attack circuits, these which we haven't yet, that's how you'll see it. So up is the high voltage, low is the low voltage. And so for PNP, if I'm going to make a PNP device, I'm going to have my P plus at the top. And this is going to be my emitter. So I'm going to have to eliminate the C right there. That E will go away. There's a lot of things that I have to change, so you do have a chance to catch up to me if you're taking notes. I also have to change these here. Okay, so I've got a P plus emitter. I have an N-type base now, where it's PNP. And I have a P-type collector. Right, it's just the opposite of the NPN device. So let me even turn these diodes around. I'm basically making diodes in the opposite direction now. But it's still essentially a device that will operate in a similar fashion. Okay, those are my diodes, and I guess I even have to change my junction here. This is now emitter base. And that's the collector base junction. This is very painful, folks, having to change all this stuff. I didn't realize it'd be this painful. But okay, and so let me finish this picture here. And so now I'm going to have my emitter up here. I'm going to have my collector down here. This is now going to be my collector current. That's going to be my emitter current. And my base current is going to be usually taken, in this case, going out of this. Okay, so that on the left is my PNP transistor. So this is a good thing to do because you're basically seeing me transform this in real time from the NPN to the PNP. So you're seeing explicitly what the differences are. And so on the actual circuit diagram on this side, I guess I have to turn this voltage around and turn this voltage around. And so I'll be applying VEB here. And I'll be applying VCB here. And what else? Yes, this will now be the emitter. This will now be the collector. And the arrow for a PNP device, and this is how you tell the difference on a circuit diagram between NPN and PNP, the arrow is going down in that direction, okay, from the top. Okay, so this is now a PNP device. You can sort of compare and contrast what you have on both sides there. They look the same, it's just you replace the P's and the N's in both of these devices. Okay, so that's device structure. Why am I going through all this for you? Mainly because what we really want to do is think how this operates. How does something with back-to-back diodes operate as a transistor? So remember what a transistor is supposed to do. It's supposed to allow you to control how much current flows between two terminals. And so the two terminals you're controlling current is between the collector and the emitter. Okay? And the base is now what used to be the gate in the MOS transistor here. So if I change that base voltage relative to some of the other voltages, I should be able to shut the device off, so there's no current flowing. I should be able to make current flow at a certain amount, and I should be able to get a lot of current flowing if I put a large enough voltage across it. Okay, so let's see how this device actually does that. And let's first talk about regions of operation. So maybe the easiest way to describe what happens in this is to look at its regions of operation. So regions of BJT operation. And for this, I'm going to make a little table. Okay, I'm going to talk about the emitter base junction, and this is for NPN I'm going to do, and the collector base junction, and what mode I end up with if I bias these junctions a certain way. Okay, and so let me say F means forward bias. You don't know what that means yet, but R means reverse bias. You kind of know what that means already because I talked about that with diodes. Maybe you know what forward bias means too, because I probably used that term when I talked about diodes as well. Forward bias means you've turned the diode on. Reverse bias means you've shut the diode off. Right? From your diode experience. Question?
The voltage sources on the diagram on the left, those are switched or
oh, I didn't draw those in, did I? Yeah, so they should be the same as the one on the right. So yeah, this should be, and you're right, even the plus and the minus need to be switched. So I got to go plus, minus, and that should be VBC. Or sorry, but VEB. And this one needs to be minus, plus, and VCB. Thanks. Yes?
On the right side diagram, should the IC current
Yeah, you're right. I forgot to change that. Or did I even write it that way? Hopefully I didn't. But yeah, you're right. Okay? All right. Another one? That's just the direction of positive current when you actually use the transistor. So usually with devices, the convention is you take the currents going into the terminals. Usually that's what you do, but when you're working with a transistor, because currents always flow down, so the way this is really going to look like is something like this, where you have your transistor. I'm going to have some voltage VCC up here. I'm going to have some resistor. Then I'm going to have my transistor. If it's a PNP, then it's going to be like that. That'll be ground, and I'll put some voltage on my base. Right? And so in this case, I'm interested in currents going down that way. Okay? And so for the PNP, that'll be IE, and that'll be IC. Because currents always go from the high voltage to the low voltage. Right? And so in this case, for a PNP, this is the way it'll look like, and that's how the voltages will look like there. So that's why I take all the currents going down. You see what I'm doing on both cases? I'm taking all the currents going down on the NPN case and the PNP case. I'm just taking the currents going down is all I'm doing. Okay? All right, so let's go back to this. So if I go back and let's look at my NPN transistor here, it actually will be the same for both of them, similar for both of them here. But for my NPN transistor, if I reverse bias the emitter base junction, it means I turn off that diode, and I reverse bias the collector base junction at the top here, right, then what's happening? Then I have no current flowing. So if I do R there, let me go back to black color here. So if I reverse bias this and reverse bias that, then I'm in what's called cutoff. It's very similar to the cutoff for MOS. Right? No current can flow between these two junctions because both those diodes are off. Make sense? Yes. Okay? And so let me just write both diodes off. Okay, now what if I forward bias the emitter base junction? So I'm forward biasing this junction down here, but I keep the other junction reverse biased. Okay? Now what's going to happen? Now current's going to flow through this bottom diode. Okay, and as I'll show, that will still allow current to flow through this diode up here, even though it's reverse biased. Okay, and so I'll show that in a second here, but just let me identify this mode as forward active. Okay, and so this is the mode that's widely used in analog amplifiers. So I would say that all of the bipolar junction transistors in your 741 are operating in the forward active region. Okay? Then I can choose some other things. I can reverse bias the emitter base junction down here and forward bias the collector base junction. That will also allow current to flow, but that's not what I want. Okay? In that case, current would flow up for this, but I would have to put a larger voltage down here as up there. And usually I'm not doing that. So usually I'm not using this mode, but I'm just saying that this also current flows. So that's the reverse active current flows in that mode there. And then finally, I can forward bias both junctions. Okay, if I forward bias both junctions, I get what's called saturation. Now, intuitively, immediately you'll think, oh, forward bias both junctions, that's the best, right? I'm going to get the most current out of that, right? That's the best. It's not, actually. You never want to see this happen in your analog amplifiers, and I'll tell you why. Okay, you always want it in the forward active region. This is the golden space right there. You want that. Okay, and you'll see that soon. But before doing that, we have to go through a lot more other stuff. So another way to look at all this stuff, you know, I can create this table that I've just created there, but I can also make a graph. Right? So if I make a graph and I plot VBE versus VBC, right, then I can look at the different regions of operation. Okay? For an NPN transistor, this region would be saturation. Right? Positive voltages across both of those junctions on, that's saturation. Okay? This region here with the VBE off and the VBC on, this is our reverse active region. Okay? And then so on and so forth. Both of them off, that's cutoff. And finally, VBE on, VBC off, that's forward active. Okay? And so all this that I'm showing here is for an NPN transistor. But I can easily do this for a PNP transistor. So I could put in parentheses PNP if I just change these voltages to VCB and VEB. For my PNP. So let me finish the NPN like that. Okay, so I can use this chart to look at both of these, but I think it's pretty simple to figure out what's going to be in what region. Okay? So now let's take a closer look at the regions of operation. And I'm going to do something else now that you always love, which is me using prepared slides for this, for some of this, right? Because this stuff, right, if I keep drawing, this is pretty simple. Well, initially it's simple. You can stare at this for a while here, but I don't want to spend a lot of time writing here. But there's a cutoff region. Okay, so what's the cutoff region? That's where I'm reverse biasing both junctions. So these diodes are both off. And if both of these diodes are off, so that means I'm putting a negative voltage across VBE. I'm putting a negative voltage across VBC. And what happens in this case? Both diodes reverse bias. No current can flow between the emitter and the collector. Okay, very little current even flows into the base as well. So I could say IB equals 0, IC equals 0, IE equals 0. You know better than that. You know that in reality there's a finite amount of current that's flowing. There's a reverse current that flows through these diodes even when they're reverse biased. Okay, but my approximation here is basically the currents are 0. Okay, and that's a good approximation if you have this transistor in a circuit with other transistors that will have a lot more current flowing. Okay? So that's the reverse active region, and that's pretty much it. If I wanted to create an equivalent model for the reverse active region, then I could do this. And so there's my NPN transistor. And like I did for MOS, I'm going to focus on NPN transistors in a lot of this discussion. You're going to have to get experience with PNP transistors to get familiar with them. Right? But in lecture, I'm only going to do NPN. I guess the book will do PNP as well. But even the book kind of just, brushes PNP, right? Everyone just does NPN, brushes PNP a bit, and it's up to you to get the experience with the PNP devices. All right, so in this case, there's my NPN device. I can equate that to just this, that open circuit on all terminals. Okay, if I wanted to be really accurate, right, if I wanted a bad grade in this class, I could use this model here, which models the saturation currents for reverse bias diodes. Right, there's going to be tiny little currents, right? There's going to be femtoamps or less currents there. And if you spend all your time, worrying about those femtoamps, you will get a bad grade in this class. I'll just be blunt. Right? You need to be able to approximate this away. All right? And so that's a model for this reverse biased. Okay? For cutoff right there. All right? And so let me move forward here and go to the next region of operation, which is forward active. Now in this region, like I said, this is the most important region of operation. I'm going to spend the most time here, showing you exactly what's happening. This is where the physics is that you're going to want to understand here. All right, so I have forward active region for an NPN transistor. In forward active, again, the base emitter junction is forward biased. That means the diode is on. So here, my emitter is here. Let me write some of that in. So that's my emitter. This is my base. This is my collector. Okay. And so in the emitter, it's an NPN device. So this is an N plus doped, and it's doped to NDE, the concentration. You're familiar with these things from diodes. Everything here is the same as diodes. So if you didn't understand diodes the first time, what you'll find in life is that when you learn something twice, you really learn it. Okay? You learn it once, maybe you know it a bit. When you learn it twice, you really know it. This is your chance to learn it twice. This is just diodes all over again. Okay? And so this is one diode here. And so there's my P, I guess I'm calling this P plus here. It could be P, it could be P plus. All right? And then finally, the collector, I'm calling it N type. A lot of times you'll make that N minus. And so what you're seeing here, remember the MOS device was purely symmetric? I had an N plus and a gate over that whole thing. This is not. I could make it purely symmetric if I wanted to. I can make this N plus and that P plus, and these N's have the same concentration. I don't want to do that. I don't want to do that because the performance of this device is better in one direction, the forward active direction, if I make this N plus and I make that N. If I have a lighter doping in the collector than I have in the emitter, I get a better device. And I will tell you why later on. It has to do with the current gain, which we'll assign a constant beta to. So beta will be your current gain. And that's maximized if I make this N plus and I make that N. That simple. And I'll give you the equation for that a little later on. But right now, let's take a look at how this device works. So the simple picture here is that, I'll live with that. I don't like the way that NAB is sticking out in there because it's going to get in my way, but I'll just run over it when I draw things. But the simple picture is that I've turned on this base to emitter junction. What does that mean? I'm forward biasing. That means I've got electrons flowing from this N plus region to the P plus region. Right? They're injected into the P plus region, and you know that that's an exponential function that they inject in. But once they inject into this P plus region, they come against this depletion region. So I should say all of these things here, I'll use green for that. This right here and this right here, you know what these are. These are depletion regions. Straight from your understanding of diodes. Right? And so you know the type of charge you're going to get in this depletion region. If this base is P-type material, right, what kind of charge do I have in the depletion region on this side? Positive, negative? P-side will be negative, right. Great. That could have been a question I put on the exam as one of those short answers. Right? So that's the kind of physics question you might expect. So yes, P side is negative here. I have negative charge at that depletion region. Then on the N-type side, of course, I'm going to have positive. Why is it negative? It's because to create that depletion region, I push holes away. I pushed away positive charge. On the N-type part, I pushed away negative charge. So this is going to end up being positive. Positive static charge. This is now creating a field, right? So my electric field generated by this is in that direction. If I have electrons flowing from my emitter into my base, and they come across this, and they see a field going in the left direction, which way do the electrons want to go? The right direction, right? They go against that field direction. So if I push electrons from my emitter to my base, they're going to want to go all the way over into my collector. They land in the base, they see that field that I have on my collector base junction, and that field just sweeps them out into the collector. Okay? If you're a transistor designer, you love that. Right? Electrons injected into the base, swept into the collector there. Unfortunately, not all of your electrons successfully make it to the collector. Because think of what's happening. You've got electrons that are sweeping through the base. Once they get into the base, what do they meet? Holes. Right? A base is just a cloud of holes because it's been P-type doped. So you got these holes around, and there's all these opportunities for electrons to fall into a hole and get stuck there. Okay? And so that happens. They recombine with holes. And where are those holes coming from? In order for them to recombine, there has to be current flow. Well, the holes come from the base terminal. They come from your supply and the base terminal. The electrons, in fact, are coming from your supply and the emitter terminal. Okay, so if I wanted to illustrate that recombination of electrons and holes, this is what happens. Electrons come here. So these are some more electrons. And then I've got holes coming from the base. Those are holes. And in the base, they recombine. So that's recombination of electrons and holes. So that creates base current and creates part of the emitter current here. Okay, you may say, hey, that's great, we get base current. No, that's not great. Because the base current is supposed to just be our control. And we don't want any voltages or currents to be on the base node. Well, we're going to put a voltage on the base node. We want to control that voltage. But we don't want current to flow into our base. Right? We'd rather have an MOS transistor where no current flows in. But unfortunately, current does flow in. That is the source of your IB in your op amps. Right? That input base current, this is it. Right here. You want that as small as possible. So you don't want this recombination to be happening, but it happens. Okay, you just have to live with it. And you can design your device to try to decrease it as much as possible. I'll show you an equation that you can use to tell me what you need in the physics to decrease this base current there. Okay? But if you had no recombination, you'd be overjoyed because then all your electrons would make it to the collector, and that, in fact, is what a transistor is supposed to do. Right? It's supposed to get current from one side to the other without losing any of it. The MOS does that without losing any of it, but the bipolar does not. Still, the bipolar, in the early years, was the much more popular device than the MOS. That's why your 741 is based entirely on bipolar. That's why I still teach bipolar. There are some people in this department that think we should not teach bipolar, but we still do. The reason? Most of those op-amps out there are using bipolar, the ones that you can buy and hold in your hand. Most of the circuits that you can't hold in your hand, like your Intel CPU or your cell phone circuits, and I can't even say cell phones, that's still a lot of bipolar there. But a lot of that is MOS. Okay, why did MOS take over bipolar?
No base current to drive it.
Yeah, okay, that's an advantage, but that's not why it took over. Why does anything take over? Yep, cost. That was it. It was all cost. MOS got cheaper over time because they figured out how to do it right. In the beginning, in fact, MOS came before bipolar. The concept did, but they didn't know how to do it right. And so that's why bipolar came first, and that's why a lot of your stuff out there is bipolar. If we could start over, a lot of people would like to just get rid of the bipolar. Okay? So, I'm not finished with currents. There's one more current component that occurs in here. What is it? I have a forward biased base emitter junction. There's hole current, right? If I forward bias this, not only do electrons want to go from the emitter to the base, but holes want to go from the base to the emitter. So I'm going to get a current component here that just comes out here, basically injected. I want that red, sorry. So I get a current component coming out here, and that's a hole current component. Right. So you get all those injections there, and that hole current component means that that's still also base current coming in. So you don't like that. All right. I'm not going to like that. And so let me skip a few slides here. So I'm going to do this minority carrier concentrations thing, but before doing that, let's define these different currents here. Okay, so I've got three sources of current. I've got one, electrons injected from the emitter to base. So let me label that as 1. That's my 1 current. Then I've got holes injected from the base to emitter. That's my 2 current. Hopefully you know which 2 I'm referring to there. That's hole current. That's also, well, no, that's the wrong 2. That's my recombination current. My 2 current is here. Hole injection into the emitter. And then finally I've got my 3 current, which is recombination of electrons and holes in the base. Okay? Now these currents that you're looking at, they are not drift currents. They are diffusion currents. Right? They're happening just like it happens in a diode because I have a very large difference in concentration between carriers at one location and carriers on the other location. So it is diffusion current. Right? Do you think I'm going to ask something about that on the exam? Yeah, I probably will. I want to make sure you understand the concept of diffusion versus drift. Yes?
So the current you have going from base to collector, so like that amplified current, isn't that drift current because it's caused by the field just shoving it to the other side?
Yeah, I suppose. Yeah, so there's always going to be some drift in there because you've got fields moving currents, but the current originates from the base to emitter junction. And so I'm going to call that drift current, really. And the magnitude of that current is not going to be affected by that field across the base collector. It's going to be affected by the slope of the concentration. And in fact, that's what I'm going to do right now. I guess I'll keep going till our next lecturer walks in, which he usually does. So, yes?
Real quick, so if you didn't have a voltage source there, would they just cancel out, or what was going to happen?
Voltage source where?
Anywhere, if you just disconnect all the voltage sources.
If you have no voltage sources, you get no current flow. Because the voltage source, what it does is it generates a large amount of minority carrier. So let's talk about that right now. So just this voltage that I put across the base to emitter junction, What's it doing? If I look at this now what I'm going to plot is the minority carrier concentration here. And so let me label this. Minority carrier concentration. Both of these axes refer to that. And you can see I'm separating this out into emitter, base, collector, right, just from the thing that I have up top there. And so when I put that voltage, I'm putting a positive voltage across this junction here, which is the base emitter junction. What happens when I put a positive voltage there? I get a huge amount of minority carrier concentration injected into this side. That's right, maybe that concentration is there. That's because I have a positive voltage across this junction, the base emitter junction. Okay? And I'm not writing base emitter right now because I'm trying to finish up because I know our next lecture is coming to me very soon, right? But we're over time is what I'm telling you. Okay? But this is reverse biased. There's an exponential function of a negative voltage. That's all the way down here, which means that the concentration profile in the base looks like that. That's a huge slope. That huge slope is going to push electrons in that direction, right? That's drift current. We'll go through the math next time, but that's going to push the electrons in that direction because of the difference in concentration. Okay, so last time we started doing this, and this is sort of where we left off. We're talking about the forward active region for an NPN transistor. And so this is a region where you have forward biased the base to emitter diode. And so the center's the base, the emitter's on this side here. I have forward biased that. And so let me emphasize that that's forward biased by putting a voltage across VBE. So VBE in this case is positive. And I will even say, because later on you'll see this, in general that voltage is going to be right around 0.7 volts. Okay, so that's a good thing to understand right now, and we'll understand it even more. It actually isn't 0.7 volts, it's 0.689457 volts. To me, that's 0.7 volts. If you want a good grade in this class, it's 0.7 volts to you as well. And the reason why I keep saying that, again, is because you don't want to keep worrying about exactitudes, right? You want to make approximations where necessary to get your answer much more quickly. Okay, we started talking about the currents that flow. Also, the base collector junction for forward bias is reverse biased. Okay, so when you're in forward active, you forward bias the base emitter junction, you reverse bias the base collector junction. Okay, and the reasons we kind of talked about last time, but I'll say more about that now. It's because we want certain currents to flow, and we like to suppress other currents as much as possible. So the current that we want to flow is this current right here, current number 1. Which is the current of electrons that get injected into the base. So that they start from the emitter side. They get injected into the base. And that happens because you put that 0.7 volts or more across this base to the emitter junction. You forward bias the junction. That injects electrons here to the point where the concentration of electrons is higher just at that point, right at the junction, than anywhere else in that base. Okay, and so if I go down, I started drawing that. There's the concentration of those electrons in that base, right at that base emitter junction. So this is the base emitter junction here. Let me say emitter base because the base is on that side. This is the base collector junction right there. Okay, and I forward bias this emitter base junction, base emitter junction. So that means I got a lot of electrons there. I've got fewer electrons throughout the rest of the base, and in particular at this edge of the base, because I have a reverse bias there. That now has very little electron density. Okay? And so I have a density of electrons that because of recombination in the base, you can derive, starts looking like just a straight line. Now if the base were wider, and if you're taking 130, you'll see that in actuality this is not just a straight line. This actually comes down and flattens out if you have a very wide base. Okay? But right now I want to keep it simple, and inevitably, if you're designing a bipolar transistor, you're going to make your base as thin as possible. You will not make it wide. So it will look like the straight line there. Okay? And you know what that straight line means. That means I have a concentration gradient of electrons in the base. The base majority carriers, of course, are holes because it's p-type. So these electrons are minority carriers in the base. Right? They're going to try to get across that base, and if they can get across that base, then they are going to make it to this electric field that you have between the base and the collector that's generated by this fixed static charge from the depletion region, and that electric field is just going to sweep them into the collector. Okay? And then you're going to declare success, because this is exactly what you want your transistor to do. You want your transistor to get electrons or charge from one end to the other between the emitter and the collector. Okay? So in this case, it looks like I'm getting electrons from the emitter to the collector, but in terms of current, I'm going to think of getting current from the collector to the emitter. Okay? Because electrons go the opposite direction as current. Now, at the same time, I don't want to have much current going into my base node, because my base node is supposed to be my control node. It's not supposed to have any current going through it. Just like your MOS gate has no current going through it, for this bipolar transistor, we would like it if there were no current going into the base. And unfortunately, there is. And that's why we have to worry about things like finite input bias currents into op-amps. That is a bipolar phenomenon. And that finite input bias current is exactly this current going to the base of this transistor. The input to your 741 op-amp is two bipolar transistors, the bases of two bipolar transistors, and that current is flowing because I've got this current happening. I've got electrons coming from the emitter to the base that were injected in, but before they can make it across to the collector, they recombine with some holes that were in the base. Okay, which you know is going to happen because there's a lot of holes in the base. Okay, hopefully not much of that happens. The other base current component that happens is because if I'm going to forward bias this base emitter junction, right, if I'm going to forward bias this base emitter junction, then that means I'm going to get a hole current. I'm going to inject holes to the emitter side as well, which is going to create a current, and that's base current. That's both emitter current and base current. So current number 2 here contributes to both emitter and base current. I don't like that because that's base current. I want my base current to be as small as possible. And so I have to worry about all these currents, and that's the reason why I make the emitter N+, and I make the base P or P+. This would work better if the base were P, actually. I'm showing P+, but sometimes it is P+, because you're forced to do that in fab. But I want my emitter to be the most heavily doped, because if I make the emitter heavily doped, that makes this current number 2 smaller, much smaller than this current number 1. And I'll tell you why in just a second here. And so in order to tell you why, I have to finish this picture down here. So I've already drawn the minority carrier distribution of the base, and you can see I have a slope there. And so with that slope, last time I identified all of these. This is the 1, 2, and 3. I just did that by words here, but it's all written down here for you anyway. But say I wanted to compute this collector current I sub C. All right? How would I go about computing I sub C? So that collector current is pretty much all of these electrons that make it through the base and to the collector. Okay? And so that's equal to the current that goes through the base, the current injected in the base there, and that makes it through. So not all of it will actually make it through. But I can approximate that by just computing this current of electrons through the base that is diffusion current. And so if that's diffusion current here, then I can come down here, identify this as diffusion current, and then apply the same math that you saw when we discussed diodes. So this is literally the second time you're going to see this. If you didn't understand it the first time, this is great, because now you're going to understand it the second time, I hope. Okay, now you've had a little bit of reading in your book maybe and that sort, but here it comes. This INB, which is the current of electrons in the base, that's going to be equal to the cross-sectional area of the base times that diffusion current, and I put a negative sign in front of that because it's electrons, but times this Jn sub B diffusion. Okay, remember that? And so now I'm going to expand this to be minus A times what that JNB diffusion is. It's equal to the charge that I have times a diffusion constant, DNB. So that's a diffusion constant for electrons in the base. Okay, and then that's going to be multiplied by the slope of this curve. That curve right there. So I want the slope of that curve. And the slope of that curve, I'm just going to write as the derivative of n sub p of x with respect to x. Where n sub p of x, like we said last time, is nomenclature for the electron concentration in the p-type region. Okay, exact same formula that I used for the diode. And I'm going to do exactly the same thing that I did for the diode. To get the slope of this, all I need to know is the concentration at this point and the concentration at that point. Okay, so the concentration at this point is given by statistics that I didn't go into in great detail, and I'm not going to do now either. But this would be the concentration. So if I call this point 0, and I call this point W sub B for the width of the base, okay, then the concentration N sub P B, which is for the base there, at location 0, that's just going to be equal to whatever the intrinsic concentration is, not the intrinsic concentration, but whatever the unexcited concentration of electrons are in the base is, which is going to be equal to that Ni squared divided by NAB, which is the acceptor concentration of the base, times E to the voltage VBE divided by VT, where VT was that thermal voltage we talked about. Okay, so the larger that VBE, the more electrons I'm going to have right at that point. That's a direct function of VBE. Okay. At this point right here, at WB, so I'm going to write an equation for N sub PB at WB. This is also going to be equal to whatever the background concentration of electrons is, which is that same N sub I squared over N sub AB, where N sub AB is the acceptor concentration of the base. Also times E to the voltage across that junction. The voltage across that junction is VBC over VT, but that is a negative quantity because VBC is negative, right? I take E to the negative power, and a rather big negative power maybe. What does that equal? Nearly 0. Very small. So that's why graphically I've drawn it like this. I have a large concentration at the base emitter junction to the base, and then I have a very small concentration at the base to collector junction. And so now I can evaluate this derivative here and just write this as minus Q times the cross-sectional area times D sub NB. And now I'm going to take that slope. So I'm just going to take N sub B PB at WB minus N sub PB at 0 divided by that total width of the base, okay, and then I'm going to go on and do some math here, and I'm not going to do all that math because it's going to take a lot of time, and so you will love this, but you don't want to sit here and watch me do this the whole way. This is all the math for you here. So this thing here basically goes here, right? So now we insert it into here. I've redone that math at the top then in much nicer handwriting, right? Proof that I can write much more nicely. Right? But in much nicer handwriting here, you see all of this here, all those equations that I just wrote there, and then finally the equation for the electron current going into the base. Okay? Which I am saying is this one current control, is this one thing, right? Is the current 1. Okay? And so that is the approximately the number of electrons that make it to the collector. It won't be exactly because I'm going to lose some to the base. Right? But I'm going to approximately say that that's equal to this, and so I sub S times E to this, right, I'm going to shorthand this as I sub S times E to that. I sub S is a saturation current, and you notice that I sub S is merely that. Okay? So with this physics that I've applied, I now have an equation by which I can calculate that I sub S, and if you plug in the numbers for all of these things, and all these things were defined later on, earlier, right? I defined Q and associated with diodes and that sort, so I won't redefine them. But you know the numbers for all of these things. You can calculate what I sub S is, and you're going to find that it's going to be on the order of 10 to the minus 15, 10 to the minus 16, 10 to the minus 14, somewhere around there, depending on how you've doped this transistor. But here you can see that exponential transfer function of current going into the collector for this transistor. Okay? And so I could keep going with all this. Where am I? So I could do the same thing to get the whole current number 2. Let me back off here a little bit so I can show you the picture. But this current component number 2, that's going from the base to the emitter, I could do exactly the same analysis. And so in this case, I'm going to have a concentration gradient here, but in this case, because my concentration in the emitter is so large, okay, I'm going to have that concentration where this NAB is here, right? So instead of NAB, I would have ND of emitter in that case. That's a large number. That will make this whole thing smaller for the emitter side. And so if I were to draw where that concentration is, I would draw it all the way down here. So if the electron concentration in the hole that was injected into the base, right, is all the way up here, then the whole concentration ejected into the emitter is all the way down here. Okay, and so it now is going to also have, it's going to go down as we go across the emitter, except by the time I get to the edge of the emitter, and so let me call this 0 there and call this W minus WE, that's the whole emitter length. If I assume the emitter length is big enough, okay, then this is going to actually look like this. Hopefully I can draw it well enough. It'll do that. Okay? So most of that diffusion current generation happens right here in a very small length. That's called a diffusion length within that emitter. And so that's something that you'll learn in 130, how to calculate that. It's not exactly, it sort of approximates a straight line there, but it's not exactly the straight line you would get from that point to that. Okay? And so if I do that, then I can plug in all that same math here for the whole current in the emitter. Right? Area times the diffusion current, and that would be equal to Q times A times the diffusion constant for holes in the emitter times the slope. And it's really that slope that I want to get at there. And I guess what I'm doing is I'm assuming not this. Huh? Okay. So I'll say here or LP. Maybe what I just did is a bit more confusing, but it's also more correct, so I'll keep it. Right. But this is or LP for a long emitter. This that I've written here is for a short emitter. In which case the denominator of this, when you take the slope, is just the total width of the emitter from 0 to WE here. Okay? Does that make sense what I just did? Okay, some people are actually saying yes, so that's encouraging to me. Now that's good. It is kind of confusing here because, right, this WE would be, actually I could do this, it's color-coded, right? So WE would be if I assumed this variation of minority carriers, holes in the emitter. Okay, whereas LP would be if I assumed this variation, which is what it would take if the emitter were long, if the emitter width were large. Okay, and then I can go on and finish off that math, which you don't want to see me do, so I've done it already. I'm going to end up with a similar current equation, almost identical to the current equation that I had for electrons into the base. So you look at these two equations, INB here, IPE, they're identical equations. The only difference is that in the IPE equation, holes in the emitter, I'm using the emitter width, and I'm using the concentration NDE in the emitter instead of the concentration NAB of acceptors in the base. Okay? Now there's a big difference here though, because this concentration NDE in the emitter is much larger than this concentration NAB in the base. Okay, remember that. Because what that means is that this current IPE is much less than this current INB, which is exactly what we want for reasons I will show in just a second. But before doing that, there's one more current we have to worry about, and that is the recombination current in the base. And I have that as well here. So this is stuff that I'm throwing at you, I understand. Right? Your book talks a little bit about this, but it doesn't really go into the depth that you really would want to understand this if you were a physicist. So you want to take 130 to understand this in more detail here. But I can at least explain somewhat what's going on with this recombination current. So this recombination current has to do with, again, it's these electrons that are being injected from the emitter to the base. You want them to go all the way across the base and reach the collector, but what actually happens is they recombine with holes in the base. And so if you think of the physics of this, I've got some electrons going through the base. And anytime I have something trying to pass, say this electron, say this is a big atom right here. I've got an electron trying to pass that atom. Right? So this electron will make a right pass. This one will be influenced by that atom a bit. This one will hit that atom right there. Okay? So you can think of it as a capture cross-section. Right? And so that capture cross-section depends on a couple things. So logically, what's one thing it'll depend on? It'll depend on the concentration, the total number of electrons you have in the base. Right? If I got a lot of electrons, I'm going to get a lot of recombination. If I have fewer electrons, I get less recombination. So logically, this recombination current, IRB, it needs to be a function of the minority carrier charge in the base, that total minority carrier charge. And if I were to look at that in this plot right here, let me use green, then that total minority carrier charge is going to be just the area under this curve. That's my Q sub E, right there. Okay? And so to calculate that, I'm literally just going to take 1/2 N sub P B at 0, which is that point, WB, which is the area under that curve. You see that? Multiply by Q times A, that's QE. And then I'm going to divide that by a minority carrier lifetime in the base. That is a function of the capture cross-section. Okay? It's going to be different for different types of bases and that sort of thing, but it's a time. It's in seconds. Okay? So that gives you a little bit physically what's going on here. It doesn't tell you the exact deep story. If you want the exact deep story, take 130. Actually, maybe 230 is where you'll learn a lot of this stuff. But this arms you with enough to understand what's going on right here, and that's all you really need to do a lot of circuit design. Actually, to tell the truth, for circuit design, you don't even need this. But it is good for you to understand this, right? Because, yeah, let me correct that. If you're really doing circuit design, you probably need to do layout at the same time. And if you're going to lay out correctly, you need to understand what sizes things need to be. This is something you do want to know about. Okay? And so, why do I care so much about this? It's because the current gain of this amplifier, this transistor, which is the main thing that I care about. I'm caring about gain. Right? Our op-amps give us gain. That allows us to do all sorts of different functions. I got to get gain somewhere from our transistors. And so, here's my gain. But for a bipolar transistor, I care about current gain. The current gain for a bipolar transistor is the collector current divided by the base current. And that's equal to current 1 divided by currents 3 plus 2, as I've defined them here. Current 1 is the injected electron current in the base that makes it to the collector. Current 3 and 2 are the recombination current, this current right here, which you can see is 3, plus 2, that injected charge and then diffusion current that occurs in the emitter from the base. Okay? And if I put all these equations together, I can then come up with an expression for this beta F, which you can see depends on these doping concentrations, NDE and NAB. This whole thing is to the -1, right? And so if I want beta F to be large, which I do, I want it to be 100 or 200 or something like that. You'll see this very plainly in your lab number 4 when you get to it. You'll actually measure it in your lab number 4. But you want that to be large. And so in order to make that large, remember there's a -1 out here to the -1 power there. I want NDE to be much bigger than NAB. That's why I've got the N plus on my emitter. And I really ought to have a P on my base. But I have a P plus, but hopefully my N plus is bigger than my P plus. Yes?
Can you clarify, so how does, in the base, when you have the recombination with the electrons and the holes, how does that result in more current out of the base?
Well, that current for the recombination, I mean, current doesn't come from nowhere. All of this current is coming from these supplies. Yeah, so that current has to come from the supply, which means it's got to enter through the base terminal. All those holes that meet those electrons, if I've got electrons coming from this terminal here, in that way, if they recombine with holes in the base, that base has got to supply those holes somehow. And it's supplying them from this terminal right here. Right, so that's base current as well. All those together are base current. Okay, so this physically is what you'll use to calculate beta F. Now, whether you do that in that, yeah, we'll make you do that at some point in this class. It's some homework assignment or so. But, when you're doing circuit design, you're never calculating this stuff. When you're just doing brute circuit design, but if you're trying to create a product that's, getting past someone else's product, you probably need to think about this. Yes?
The tau variable for the carrier lifetime, is that usually a thing of a property that's given, or is this something calculated?
That's something that's usually measured, so I'll say given, yeah. Something that's measured. You could try to calculate it, but there's physics that say what it is. And that's based on, the capture cross-section of your atoms and that sort of thing, which really comes down to the physics of the atoms. How many, where is its valence shell, that sort of thing. So you could try to calculate that, but you're going to trust that. So in general, what happens is people will measure it and you'll use those measured numbers. And then calculated theoretical numbers get close to that. Okay, you'll be given that, is the short answer. Yes?
You mentioned that having a smaller doping concentration in the collector is also beneficial.
Yes. So that comes in by just the depletion region in this. I'll talk about that later on, actually, when I talk about how that factors into this whole thing. And so let me also complete this picture here. What do you think the minority carrier distribution looks like in the collector? What does it have to be at this point here? Or sorry, I already pointed at it, so it's right there, right? Because I've got a reverse bias across the collector-base junction. But out here, the current's going to be somewhere around there, which is going to be the equilibrium current, or not current, but charge concentration, right? That's the whole concentration current in this. And so, in the end, it'll look like that. Okay, just to finish the current distributions that I have in all of these things. All right, and so with this thing, with the forward current gain, I could say more about what maximizes it. And so that's right here. So to maximize beta F, I want WB to be small. I can just see from this equation here, right? I want the width of the base to be small. That's why I've made my base very small. I want the concentration of my emitter to be much larger than that of my base. I just said that. And I want tau B to be large. Right, tau B being large means that the electron in the base survives a much longer time. That's approximately what that means. It can sit in the base for a longer amount of time, which means it won't recombine very quickly.